In today's lesson, we're going to be looking at the rational root test. So we had seen earlier when you're factoring polynomials, sometimes you're using synthetic division and you're trying integers plus or minus 1, plus or minus 2, plus or minus 3. It's not working. There are situations where you have a polynomial, a higher order polynomial, and that polynomial has roots that are rational. So let's say you have a root at 1/3, 7/8, whatever that may be. That's a rational root, and that's not a value you would think to check. So using the rational root test, what we can get is a complete list of possible roots that the polynomial will have, which are either integer roots or rational roots. Let's take a look at how you would do this. Well, the definition is, suppose we start off with a polynomial, higher order polynomial, where all these coefficients are integer values. And what we want to do is consider the number c over d. So c over d is going to be a fraction in lowest terms. If that fraction c over d is in fact a root of the polynomial, it must be the case, and this is what the rational root test is saying, is that your c value must be a factor of your constant term, in this case a naught, and your d value must be a factor of your leading coefficient an. So let's take a look at an example. We can see the rational root test being applied. For this example here, using the rational root test, what we know is that if this polynomial has a rational root or an integer root, it would be of the form c over d, where our c value is going to be a factor of -4, and our d value is going to be a factor of 3. So step number 1 is to write all the factors of, in this case, for our c value, is going to be all the factors of -4. So we have plus or minus 1, plus or minus 2, and plus or minus 4. These are all the integers that divide -4. Likewise, we have our values d, and d will be all the factors of our leading coefficient, in this case 3. So we're going to have plus or minus 1 and plus or minus 3. Putting these together, c over d represents all possible combinations of integers or rational expressions, which could be factors of our polynomial. So to do this here, we take our plus or minus 1 divided by plus or minus 1 is just going to give you two roots, either 1 or -1. Then we take our 1 divided by plus or minus 3. So plus or minus 1 divided by plus or minus 3 creates two possible roots, plus or minus 1/3. And then we move on to plus or minus 2 divided by plus or minus 1. Again, that'll create two possibilities, in this case plus or minus 2. And then we have plus or minus 2 divided by plus or minus 3. Again, creates two possibilities, plus or minus 2/3. And then lastly, plus or minus 4 divided by plus or minus 4 will create plus or minus 4. Plus or minus 4 divided by plus or minus 3 will create plus or minus 4/3. So therefore, the following polynomial, if it has integer or rational roots, will be from this list here. So you can see here we save some time. I don't have to check plus or minus 3 as it's not on the list. I know that beyond plus or minus 4, we're not going to find any integer roots. If there are rational roots, it would be either plus or minus 1/3, plus or minus 2/3, or plus or minus 4/3. Let's take a look at decomposing this polynomial using our rational root test. You can see here by looking at the list of possible rational roots, I tried 1, in which case it didn't work. -1 actually was a root, and I was able to decompose my polynomial. We're now going to focus on this factor of our polynomial and try to find other roots, again going back to our rational root test here. Let's go ahead and do that. So again, going through our rational root test list here, you can see I tried 1/3, did not work. I tried minus 1/3, did not work. I tried 2/3 and I got it to work. So now our polynomial decomposes as follows. Let's take a look here and see what type of roots we would have. Checking the discriminant we get. So checking this here, you'll notice that the discriminant is 72, not a perfect square. So therefore, this part of the polynomial has irrational roots. So we can see here we had a higher order polynomial of degree 4, which had a root at -1, 2/3, and then irrational roots. This would be an example where we would have no other choice to break the polynomial down. We could have done synthetic division and found the root at -1, but we definitely would have needed the rational root test to discover 2/3 as a possible root to check. Let's take a look at another example. So for the following example here, what we want to do is apply the rational root test. We have here constant term of 20. So using the rational root test, our C value is going to be all the factors of our constant term. In this case, it'll be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10. Our D value here will be all factors of our leading coefficient, which will just be plus or minus 1. So therefore, using the rational root test, a complete list of possible roots for our polynomial here will be, so again, to remind you of the rational root test, how it works is this represents a complete list of possible rational roots the polynomial may have. This polynomial could have complex roots or could have irrational roots, as we saw in the previous example, that will not show up in our rational root test. So if our polynomial has rational roots, it's in this list here. Examining this further here, we'll see that the coefficients of this polynomial are all positive. Therefore, any of these positive roots here, 1, 2, 4, 5, or 10, when substituted into our polynomial, can never equal 0. Therefore, we can reduce this list further to become just focusing on the negative values here. So as you can see here, like we're discussing, any one of the positive values, if you substitute those in here, because all the coefficients of our polynomial were positive, there's no way for that to yield an answer of 0, so a root. So in this situation here, the only possibilities there are, if this polynomial has a rational root, it must be from these 5 values. Let's check this using synthetic division. So evaluating our polynomial at the list of possible rational roots we see here that if I check this at 1, -2, or -4 did not work. However, checking this at -5, we actually got a root. And again, that was in our list of using the rational root test. So the following polynomial does have a rational root, and that rational root is at -5. The other 2 roots are either complex roots or irrational roots. And just looking at our polynomial a little bit closer here, we can see I just decomposed it. You have your x plus 5, and you're left with x squared plus 4. This has no real roots, right? X squared plus 4 does not cross the x-axis and yields no real roots. All right, let's take a look at another example. Following example here, let's take a look at a complete list of possible rational roots for the following polynomial. So again, looking at C, we're going to take all the factors of our constant term, in this case plus or minus 1, plus or minus 2. Our D value would be all the factors of our leading coefficient, in this case plus or minus 1, plus or minus 3, plus or minus 5, or plus or minus 15. Combining these together, we get a complete list of possible rational roots for our degree 6 polynomial, and they will be, so fairly extensive list of possible rational roots. And again, making the same observation here, these leading coefficients are all positive. Therefore, it's impossible to substitute any positive roots in and get a remainder of 0. So therefore, we can eliminate all the positive values. So we've cut our work down in half now. You still have a fair bit to check regarding this here, but if you wanted to continue this, you could check all 8 of these and see if you get a rational root. All right, let's take a look at another example. In the next example here, same idea, we want to find roots of this polynomial. So using the rational root test here, we can find all the factors of 12. In this case, this will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, or plus or minus 12. And the D value is all factors of our leading coefficient will just be plus or minus 1. So therefore, the C over D values will be as follows. And again here, checking this out here, we have a complete list of possible rational roots that the polynomial has. Notice again, the coefficients here are not all positive or not all negative, so we can't eliminate half of these. You would have to check all of these here and hope that one of these breaks down our polynomial. Let's take a look at this using synthetic division. So as a further observation here, when you actually go ahead and do synthetic division on these and check them out here, none of these end up working. So the conclusion here is that the polynomial p at x has no rational roots. However, because the degree of our polynomial is odd, you can see it is of degree 7, we know it crosses the x-axis. If it crosses the x-axis, it must have a real root, so that root must be irrational. So this polynomial of degree 7, using our rational root test, we were able to discover that it has an irrational root. It has no rational roots, as none of these worked using synthetic division, but because the degree is odd, it has an irrational root. All right, that concludes today's lesson on the rational root test.